So hi, good evening. This is week 2 of NPTEL course Introduction to Algebraic Geometry and Commutative Algebra. This is a course under Dr. Dilip Kumar Patil. Okay, so this week topic is module theory. So let us go through the module structures first, then we'll start doing assignments provided by the professor. So yeah, let A be a ring and V be an additive abelian group. If there exists an you can call it an action of A on V like this, like A comma X goes to A dot X or AX is an operation of the multiplicative monoid of A on V as a monoid of group homomorphism. That is, you can say that these elements of A gives a homomorphism or endomorphism of V. This A goes to this mathcal VA, and such that X going to AX is a homomorphism of the monoid into the multiplicative monoid NV, comma the operation of the endomorphism ring. So then since already you know that endomorphism of V is a ring, we talked about this in the last class. It is natural to consider such an operation of A which is even a ring homomorphism. That means if we can make this homomorphism into a ring homomorphism, and in other words, an additive abelian group, that means the operation is addition and the operation is also abelian, that is commutative, together with this operation, or you can say action, is called a left-a module. That means that it is closed under this scalar multiplication, and also that there is the distributive property that holds well, and yeah, and this homomorphism is a ring homomorphism. So what we say is that V is a left-a module if the corresponding action homomorphism is a ring homomorphism. That means it so the where is the distributive property coming? That means your V of AB will be V of A dot V of B. That means it will behave well with the multiplication and the addition and all the other things that comes with the ring homomorphism, and equivalently you can say these properties hold. So I won't break down how these two things, that is ring homomorphism and these properties, behave them in between themselves. You can check it yourself. So I can just write it, check equivalently. So what are these identities? That is AB of AX is A of BX, A of X plus Y should be AX plus AY, and AB plus X should be X plus BX, and the one that is coming from the ring 1 of X should be X. And so on the ring A itself there are two module structures which are compatible in the following sense. That is, you can consider A as an abelian group, and since A is a ring, you can consider A as an abelian group. Therefore you can consider A as an A module, and since we have not talking about this considering left module and right module as a module, so yeah, there will be these compatible things that you can write. Yeah, so we should directly go to the this tautological module structure on an abelian group. That is, if W plus be an abelian group, then you know it is already a Z, it should be a Z module. How it should be a Z module? Because it is an abelian group, so there should be an action of Z over W by this, like you can say to W. So z comma w should go to z of w. Since there is a group operation in w, you can write this as w plus w of z copies. So yeah, it has a natural z module structure. And also what it said here, that the identity ring homomorphism defines the so-called NW module structure on W plus. That is another thing, that there are two kind of tautological module structure. One is here and other is that you can say that end of W plus acting, I should write it like this, W going to W, and how, that is f dot x should go to f of x. This is clear, right? Okay, so now we come to our first question, that is we have to prove that if u is contained in W, and so I should first say what is u and W. I'll try to find if it is given here. Okay, so maybe I will go to this Dropbox and okay, so what they have said, that u w u prime w prime are sub modules of R module V. So I should write it here, u v w and w prime are submodules of R module W. Yeah,
It should be u prime, right?
yeah, u prime, it should be u prime, and this should be V. Okay, so these are fairly straightforward things to follow, but yeah, we will discuss this. That it said that if u is a submodule of W, then W intersection u plus u prime should be equals to u plus W intersection u prime. Now we will prove the both inclusions. So first we will show this forward direction. Now let us consider this x, which belongs to u plus W intersection u prime, and then you can write x as u plus y, where u belongs to small u belongs to capital U, and small y belongs to capital W intersection capital U prime. And since y belongs to small y belongs to W intersection U prime, we have that y belongs to both of them. And now to show x belongs to W, since small u belongs to capital U, and which is already a subset of W, you can say that y belongs to W, and the W is a sum module, so therefore it is closed under addition. So you can say that x belongs to W, right? And to show that x belongs to u plus u prime, we have that since small u belongs to capital U and small y belongs to capital U prime, we have x equals to u plus y. So this belongs to capital U plus capital U prime. Therefore since x belongs to both W and u plus u prime, we have that x belongs to both of their intersection, and which proves that this one direction is complete. And in a similar way you can show that the other direction is also true. Now, so let us assume that x belongs to this intersection, that is w intersection u plus u prime. Then x belongs to w and x belongs to u plus u prime, and since x belongs to u plus u prime, you can write it in this form where these elements are coming from these, and we need to show that x belongs to u plus w intersection u prime. So to do this, we will show that this u prime belongs to w, which will imply that u prime belongs to w intersection u prime, right? Because u prime already, small u prime already belongs to capital U prime. Now, since x belongs to w, we have, and x belongs to u plus u prime, we have that u plus u prime belongs to w, and since small u belongs to capital U and which already a subset of w, their their subtraction x minus u belongs to w, right? I mean minus u belongs to w because w is a sum module, and u belongs to, small u belongs to capital W, therefore minus u belongs to capital W, and therefore your u prime is x minus u, which belongs to capital W, and w is closed under addition, right? And since small u prime belongs to capital U prime and small u prime belongs to w, we have that u prime belongs to their intersection, and therefore this happens, and that is that x belongs to your this sum, and which proves that this inclusion also true. Therefore we conclude that they are equal. Now we come to the second problem, that is if u intersection w and u prime intersection w prime, then we have that u equals to this u plus w intersection u prime intersection u plus w intersection w prime. So yeah, now let us assume that this intersection is called by D, that is u intersection w and u prime intersection w prime. So we probe we'll show that by inclusion, obviously both the inclusions. First we will show that every element of u belongs to this this element, this thing. So let small u belongs to capital U. Then you can say that u can be written as u plus 0, therefore it belongs to this, and also similarly this. So therefore what you can write is that this inclusion is trivial, right? Because there is nothing to show. Now next what will show that any element from this thing belongs to capital U. So we start with small x from this thing, and then since small x belongs to u plus w intersection u prime, you can write in this form, or your u1 belongs to capital U and small y1 belongs to w intersection u prime, and again from here that x belongs to capital U plus w intersection w prime. So similarly you can write it in this way, where elements are coming from this. Now from these two expression we have that since they are equal, they satisfy this, and rearranging, I mean take u to this side and y1 to this side, you will get this. And now we analyze both sides, that is u1 minus u2 belongs to u, right? Since both of them belongs to u and u is a sum module. So therefore and also one thing to notice is that small y1 belongs to this intersection and small y2 belongs to this intersection. Now therefore what happens is that small yn belongs to capital W and small y2 belongs to capital W. Therefore their intersection is also in W, I mean their difference. So since u1 minus u2 belongs to u intersection W, how are you getting it? Because this thing belongs to W and this, they are equal, so this belongs to W. So this thing belongs to u intersection W, and also u intersection u prime intersection w prime. And yeah, so earlier we had that u1 minus u2 belongs to this and this, and this belongs to, sorry, u prime, so therefore we have this. And also since y1 belongs to u prime and this belongs to u prime, and u prime is a sum module, this element belongs to u prime, but y1 plus u1 minus u2 can be written in this form, this y1 plus y2 minus y1, because this is getting subtracted by this, so which is y2. So what I am trying to say is that this is really like rigorous. Okay, better than me telling this, you should look into it and give it a thoughtful read. This is fairly straightforward, and I am since I am talking this much, I am losing what I am telling. So you can just read it and you will see that this x belongs to u. The proof is well written, so you can just look into it and find it. Is it okay? It's just checking of these digits and elements.
Yeah, I think this requires some manual work, so I think we can do it.
Yeah. Okay. So yeah. Okay, let me do this then. Question 2.4 says that let u and w be a submodules of the A module V. Then the following are canonical isomorphisms, that is u intersection u mod u intersection w is isomorphic to u plus w by w. And the second thing that says that if u is contained in w, then we can say that v mod w is isomorphic to v mod u mod w mod u. So these are, you know, that these are called classical isomorphism theorems. You have seen this in in group theory, also in ring theory. So there is an analogous result for also module theory. So first let us focus on the problem 1, that is u mod u intersection w is isomorphic to u plus w by w. So let us first define the map, this phi from u to u plus w by w by u going to u plus w, right? Because small u is already element of capital U plus capital W, and we see that phi is well defined. I mean, if you take small u from capital U, then we have that small u belongs to capital U plus W, since u can be written as u plus 0. Therefore the quotient is well defined in this thing. I mean, okay, so next we claim that phi is a module homomorphism. So to check a homomorphism or a morphism is a module homomorphism, it is enough to see that phi r u1 plus u2 is r of phi u1 plus phi u2, right? Something you are already familiar with. So you take two elements from capital U and smaller from capital A. Now you take phi of u1 plus u2. So as we have defined this way, this will be u1 plus u2 plus capital W, and it can be rewritten as this. Since capital W plus capital W is again capital W, so there is nothing to see new. And for the second part also, since small r capital W equals to capital W, it can be written this way. So this is a module homomorphism. Now we have to show that this is surjective. So if you take any element small x plus capital W from this, where x belongs to u plus w, then again your x should be small u plus small w for some small u belonging to capital U and small w belonging to capital W. Thus you can write this as small x plus w in this form, small u plus small w plus capital W, and since your small w belongs to capital W, this can be rewritten as this, and which is again your phi u. So yeah, phi is surjective, and the main trick is we have to find the kernel, and we will see that the kernel is exactly u intersection w. I mean, if you take small u from capital U such that phi u is 0 plus w in this, then I mean your phi u is u plus w, which is 0 plus w, right? Therefore u minus 0 belongs to capital W, right? That means u minus 0 belongs to capital W. That means u belongs to W, so you have u plus W equals to W, because phi W is a sum module. Yeah, so you already started with an element of u, and you saw that this is an element of W, so therefore at least one direction is clear, and the other direction is also fairly trivial. You can just check it yourself, because it is already, so the elements are already contained in W, so therefore it will be in kernel. So therefore the first isomorphism theorem for modules, that is the domain by kernel is isomorphic to image, we see that this is true. And for the second also, that is if u belongs to W, then this happens. So what we will do is that draw a map from this to this, and show that this this natural morphism has this as kernel. So again we draw a map from V by U to V by W, and since U is contained in W, this map is by convention this is well defined, right? Because if you take V1 plus U equals to V2 plus U, then it will be V1 minus V2 belongs to U, which is in W, so therefore you can write V1 plus W equals to V2 plus W, right? So therefore this is well defined. And also psi is a module homomorphism. Because of this you maintain this linearity, therefore there is nothing to see that nothing non-trivial to see that it is a module homomorphism. Yeah, so so one thing to prove is that psi is surjective. So for any v plus small v plus capital W from this, you will see that if you take simply just v plus W, v plus capital U, this has image this, so therefore psi is surjective. So only fairly non-trivial thing to see is that the kernel is W by U. But yeah, so if you take small v plus capital U such that this is 0, therefore this will happen. So you will see that from here you can check that if you take any v plus small w belongs to W, that is small v W equals to W prime, therefore it will be small v equals to W prime minus W. So since this is belongs to capital W, therefore this happens. And yeah, okay, so this is a typo, this should be small v, yeah. So therefore again by the first isomorphism theorem this is true. Now I'll take a 2-minute break. You should look into this and try to prove it yourself, and after 2 minutes we'll start doing this. Okay, so let us start doing this. Okay. Yeah, so that the following sequences are exact. That is if you are you familiar with the exact sequences? That is the image of the first map is equal to the kernel of the next map. Are you familiar? Then I can explain, or else I will start proving this. You can just write me down or something.
No, I'm not familiar with that.
Okay. So let me tell you what happens for an abelian group. Sorry, for a group. Then we can just simply imagine the analog thing for module. So say use G1, G and G2. This diagram is given. This is nothing like non-trivial. You just compose these maps, something like this, that 0 to G1 is a group homomorphism, G1 to G is a group homomorphism, G to G2 is a group homomorphism, and G2 to 0 is a group homomorphism. You just compose them and make it a chain. So we say it is a complex of groups if this happens, that if okay, forget the 0 thing. Say this is G2, this is G3. So make it I plus 1 and I plus 2 dot dot dot. That means there are G minus 1, I minus 1 and those kind of things also there. So you can write it as di and di plus 1. So these are group homomorphism, you can say. So it is a complex if the composition okay. So it is a complex if the composition di plus 1 circ di equals to 0. That means its image of di image of di is contained in kernel of di plus 1, right? This is interesting. Just try to focus that. Yeah. So this composition, this is 0 equivalently if this image of di is contained in kernel of di plus 1, right? You can just think about it later and let me know. So this complex is called an exact sequence if this containment is equal. That means exact if and only if, not if and only if, I am defining exact if image of di equals to kernel of di plus 1. I should have written down somewhere else, but since there is no space, but these are all fairly well known things, so you can just google it, what is an exact sequence, they'll show you. So yeah, so from complex we are coming to exact sequence. And what is a short exact sequence? Now when the exact sequence is of the form that g1 g2 g3 0, this thing is exact. Short exact sequence. So when this thing is exact means that d1 d2, first of all it has to be complex, so d2 composed d1 should be 0, and also image of d1 should be equals to kernel of d2. So this is what is happening here. So we have to show that this complex of modules, so modules meaning they have to be module homomorphisms, and also the kernel of one homomorphism should be equals to image of the previous one. The inverse thing, the image of the first homomorphism should be image of this homomorphism should be equal to kernel of this homomorphism. Okay. So now we focus on learning that these two complexes are exact or sequences are exact. We don't know if it is a complex yet, so these two sequences are exact. So maps are given by this. The maps in 1 are given by x going to x minus x comma minus x, that is x belongs to this u intersection w, and x comma y going to x plus y. And okay, we'll see, we'll talk about 2 later. So first focus on 1. These are 2 maps. Okay, so first we have to show that the first we are naming these maps, that is alpha and beta. So alpha x equals to x comma minus x, and beta of xy equals to x plus y. First we will show that these are module homomorphisms, therefore alpha of x1 plus x2 should be alpha of x1 plus alpha of x2, which is straightforward to prove. From this to this happens, and therefore it is true. And for also this is fairly straightforward. Now we have to show that one more thing I forgot to tell you, that this image of one map is kernel of the next map. Things should happen at every stoppage. So for the first one, its image is 0, right? Therefore the kernel of d1 should be 0, that means d1 should be injective. Oh my god, d1 should be injective. And for the last thing also, the image is 0 here, so therefore the kernel is all of g3. I mean, if this is d0 and if this is d3, the kernel of d3 is all of g3. Therefore the image of d2 should be all of g3. Therefore d2 should be surjective. So this is the main main mantra for short exact sequence. So our first aim is to show that this alpha is injective. That means d1 is injective. So let alpha x equals to 0 comma 0, then x minus x is 0, therefore x is 0, so alpha is injective. There is nothing to do non-trivial here. And for x1 comma y1 and x2 comma y2, did something happen here? Okay, acha. So now we will show that again beta is a group homomorphism, but that you can check, sorry, module homomorphism, so that you can check. Now what we will show that beta is surjective. So take any z from u plus w, then you can write z as u plus small w, where small u belongs to capital U and small w belongs to capital W. Therefore you can simply take small u and capital W from this direction, and by convention beta of u comma w goes to this u plus w, it is z, therefore beta is surjective. Now we will show that image of alpha equals to kernel of beta, therefore that is this condition, image of d1 equals to kernel of d2. So first we will show the forward direction, that is image of alpha is contained in kernel of beta. So you can take one element x from u intersection w such that what I have done is that I have tried to show is that beta compose alpha is 0. That is so that will imply that beta of alpha x is 0, right? Now alpha x belongs to image of alpha, and if beta of this image thing is 0, then alpha of x belongs to kernel of beta, right? Therefore image of alpha should be in kernel of beta. That is what I have done, that alpha of x equals to x comma minus x, and beta of this should be x plus minus x, which is 0. Therefore image of alpha belongs to kernel of beta. And similarly let u comma w belongs to kernel of beta, then beta of u comma w, that is u plus w, is 0. So u equals to minus w, therefore since u belongs to u, capital U, and small w belongs to capital W, therefore we have that they both belongs to both, so both belongs to u intersection capital W. Then we have u comma w is u comma minus u, which is alpha of u. So we have shown that u comma w belongs to image of alpha, so the other direction is also satisfied, therefore they are equal, so the first sequence is exact. Now we come to the second thing, but this is exactly same as first one. So I am giving showing you the diagram. Can you read it and tell me this if you are understanding this, because continuous talking making me tired, so I can also get a break. Let me know where you have a doubt or something, then we can talk about it. This is exactly analogous to first one, but little complicated since it involves the mod thing. mm, but we have already done one or two problems, the isomorphism theorems from the previous one, so we are familiar with this language.
Sir,
Yeah.
in when we take quotient with u direct sum w, v modulo u
Where
direct sum w,
so you are talking about the exact sequence?
exact sequence
Yeah.
at the middle.
Yeah.
So that you wrote like direct sum
Yeah.
of v
Yeah.
mod plus v mod w. So where what theorem we had used here, that
Like
v mod u direct sum w is isomorphic to this.
uh, I don't understand your problem. Like this one you are
So
saying?
yeah, just before it, domain of it means sorry, domain of beta prime.
Domain of beta prime. So sorry, what what is happening? Uh, one second, huh? The call got disconnected. Hi, hello.
Yes sir.
Yeah, yeah. Can you see the screen?
No sir.
I can understand. Is BNP. So showing two times. Okay. Now I'll have to share. Yeah. Now. Hello.
Yes, it's
Yeah.
visible
Yeah.
now.
Okay. Okay. Thank you.
Yes sir.
So you are talking about this domain, right?
Yes.
So your inquiry is that how it is formed or something like
No, I wanted to know, is this isomorphic to v mod u direct sum w?
V mod U direction W. If this is isomorphic,
Yeah.
uh, I mean, I'm not sure. I cannot say no, I cannot say yes. We have to check. First, we have to consider how would the map look like if we want to say it is an isomorphism as module. So we have to give it a map first. So you are saying, are you saying this that V mod U on the first summand, it should be identity map? Then V mod W to W it should be a zero map, right? Something like this, or W to V mod W. Yeah, hopefully it will not be an isomorphism. I'm not sure from where you are telling about this, but hopefully it will not be isomorphism. But if you can construct and prove it an isomorphism, I will be happy to learn. Okay.
No, actually, I means the natural question that I had was the just before we have proved
Uh-huh.
the exact for this u intersection w and u direct sum w and u plus w.
Huh?
So I just wanted to know that by quotienting, how
Quotienting with
direct
what?
quotienting means like if this is a direct sequence, it's an exact sequence. Then if we take v modulo that direct sequence in a weak term, but so is it still remains exact? Means
Okay. If you have any writing pad or anything, you can share your screen so that I know. Or if you don't have, you can just turn your camera on and show me on a note or something.
no sir, I'm outside actually. I'm unable.
Ah,
So
okay, okay,
I
okay. That is fine. That is fine. But yeah, you can send me a mail writing what you are telling when you get time, and I can look into it. I always encourage to my friends and students and everyone to discuss about these things. So if you have time, you can just write it down and send me a mail to me. Okay, so for now we can focus on this. uh, so already maps are given here. You can try to prove that this is an exact sequence. So first we have to show that both the maps are homomorphisms, uh, which are like straightforward. uh, so can we move so that we can focus on the next part?
Yes, I think we can try this one.
Yeah, yeah, it will be good.
Yeah.
So let me know when to move forward so that I can move. I can scroll.
What I meant was, I think you can move to the next question because I think we can try this
Okay,
at our
okay,
free time.
okay, okay. Then it's fine. Yeah. Okay. So we shall try this one. That is, if A is a field and U and W are subspaces of K vector space V. So from the first exact sequence, uh, yeah. So from the first exact sequence, can we say that this dimension formula follows? So one thing, this should be R. In commutative algebra, most of the time we write ring as A, so therefore this kind of typos happen. But yeah, so you know that this is the famous dimension formula, right? That dimension of u plus w is dimension of u plus dimension of w minus the intersection. And one thing to note that dimension is additive. I mean, so first of all, that you a trivial example for modules is that vector spaces over fields are modules, right? Because if you take your ring as a field, then you get the module thing. So module is kind of like generalization of the vector spaces, where you replace your field by rings. You know that field is a ring, right? Because there is multiplication and addition. So these are like beautiful observations. The more you observe, the less you fear this algebra thing. Once you kind of follow the chain of these generalizations, then you come to realize that this module, ring, group, algebra are not arbitrary. They are generalizing our previous known objects. So this algebra thing, that R algebra or A algebra, they generalize your module structure. That means
Sir, in this corollary one, like
uh,
dimension of U intersection W plus dimension of U direct sum W, or it's just U sum W? It seems,
uh, yeah, it should be like, it is fine. This one is dimension of U direction W. Now is it clear?
so the other way, okay, it seems non-trivial to me.
Which part? This part?
Yes,
This part?
this part. Yeah, this the equality of these dimensions. I think like the middle one is the quotient of,
Middle one is this.
this is the middle one.
Yeah.
Okay. So middle one is the sum of the other two, or
Yeah.
different? Okay.
By dimension is additive, I mean that the
Okay.
middle one should be the sum of the first one and second one.
Okay. Okay.
I mean, when you see that additive thing in algebra, commutative algebra, they mean that behaves well with the short exact sequence. So that the middle one should behave well with
Okay.
the first
It's
and third.
kind of like kernel goes to the group, or that image, that kernel directs some images.
Uh,
I.
so not exactly. When that happens, it called split exact sequence. So there is a name
Okay.
for that.
Mhm.
Uh, but uh, but uh, but dimension formula is kind of stronger than that. Even when it is not split, that means your kernel plus image are like, they form direction. Even when it is not true, then also dimension formula holds. So I mean, at least for this case, if you see, this is kind of uh, I mean, less worrying, right? Because it is, you understood this, right? The dimension of U direction W is dimension of U plus dimension of W. That follows from linear algebra, right?
Yes, sir. Clear, sir. Clear.
Yeah, because you are taking your basis at like this U1 comma 0 and 0 comma WJ, right? So yeah, but you are asking some interesting questions that uh, so this is kind of an exercise that you can prove that if you are given a short exact sequence of vector spaces, then you can write it uh, you can prove the dimension is additive. But what is happening here is that we are not using dimension formula, so I should not we are not using the additive formula. I should have told you this. From this, can you follow that u plus, I mean, u direction W by u intersection W is isomorphic to uh, u plus W? Can you follow this? Because
Yes.
yeah, from the isomorphism thing, and you know the dimension of uh, quotient thing is dimension son of this minus dimension of this, and since they are isomorphic, I mean, is it clear now?
Yes, sir.
Yeah, okay, nice. Okay, so similarly you can look for the corollary 2 and give me 2 minutes. Sorry. Yeah, hi. Uh, so, hi. So, did you look into it? I mean, it also follows from the second isomorphism theorem, second short exact sequence. That is, so from here, if I just copy this and paste it here. Yeah. Yeah. So can you follow this from here? So what is happening is that treat them as vector spaces, right? So dimension of v mod u direction v mod w by v mod u intersection w is dimension of v mod u plus w, right? So this implies now it will be kind of like uh, it will be kind of like this addition subtraction game. Equal to dimension of v minus dimension of plus w. Can you do it from here, or if you have already done it, you can tell me too. Yeah, it was done here. I should have noticed it. Hi, hello.
Yeah, I think it's done.
Yeah, okay. So yeah, from this you can follow this formula, right? I mean, oh, it is said about codimension, so that you have to notice. So these are all like preparing you for the coming upcoming things in the course. So codimension is very important in geometry. Well, I mean, in geometry you can think of like this: a curve has dimension 1, right? So if you look for a curve in u, I mean, look for a curve in Euclidean, say Euclidean space. Euclidean space has dimension 2 and curve has dimension 1, so the codimension should be 1, right? That is, your v should be r2 and u has dimension 1, so codimension should be 1. So yeah, I think this is clear. Okay, so let us focus on the next problem, that is, let A be a commutative ring and F from V to W be a homomorphism of A modules, and for a submodule U of V we have to prove this, that F inverse of F of U should be U plus kernel of F, and U mod U intersection kernel of F should be isomorphic to U plus kernel of F mod kernel of F, which is again isomorphic to F of U. So we first focus on the first assignment, that is F inverse F of U equals to U plus kernel of F, and again we prove this by double inclusion. So let V belongs to F inverse of F of U, then F of V equals to F of V belongs to F of capital U. So there exists small u of capital U such that F of V equals to F of U. That means F of V minus U belongs to equals to 0, which implies v minus u belongs to your kernel of f, and that will imply that v equals to u plus v of minus u, and where u belongs to capital U and v minus u should be in kernel of f, which is you have done. So therefore your v belongs to capital U plus kernel of f. So therefore one direction is proved. Now for the other direction, let small v belongs to capital U plus kernel of f, then small v equals to u plus k, where your small u belongs to capital of U and small k belongs to kernel of f. Now we have that f of v equals to f of u plus k, and since k belongs to your kernel of f, therefore it should be f of u, and f of u already belongs to f of capital U. Therefore your v belongs to, f of v belongs to f of u, therefore v belongs to f inverse of f of u, and this proves that the other inclusion also true, therefore this is true. Now again we have to prove the second thing, so I would suggest you to look into itself and see if this is, you can understand this. So the first isomorphism is true, which we have proven in 2.4 of A, which is nothing but this u mod u intersection w is isomorphic to u plus w intersect mod w. So yeah, this is true, right? So you can ignore that, just focus on the second thing. The second isomorphism. Is it okay, or do you have any doubt? If you have doubt, you can let me know and we can do this together. can we move forward if it is okay?
Okay, so in this question, did we first identify the image and then the kernel and then put it into the first isomorphic theorem again, right?
Yeah.
Okay. Okay, that's okay. I understand now this. Okay.
Yeah. Okay. Fine. So just we draw a map to W and then we take the image. Just that. Okay. So yeah, something like this happens when you understand up to this. Then you just substitute this from so image of fu of kernel f is this fu, so that you put here, and kernel of fu plus kernel of f, you have proved that here is kernel of f, so therefore this is true. Okay, now we will prove something functorial, that is if V to W is a surjective module homomorphism, then the maps phi, where phi is a map from the collection of some module U such that it contains kernel of F, and collection of some module X of W. So there is a map from U to FU, and again X is a submodule of W and U is a submodule of V, which contains kernel of F, and X maps to F inverse of X. So it is kind of this, you have studied this earlier, na, that if F is a surjective morphism, then or if F is a surjective morphism between this, so you have seen that all the subgroups containing all the subgroups in G2 have one-on correspondence with all the subgroups of G1 containing kernel. We have seen this earlier, right? So this is the generalization of this. So we will prove that they are inverse maps of each other. I mean, these are the morphisms which will make this correspondence a correspondence. So there will be a bijection between them. So first of all, did you understand the maps that from this collection that some modules containing kernel, there should be a map from U to FU. FU is a submodule of W, so there is no doubt. And if you take any W, any submodule of W, then you will see that its inverse image is a submodule, and it will contain kernel, right? Because 0 belongs to this submodule X. So therefore F inverse 0 belongs to F inverse X, and F inverse 0 is your kernel. So therefore kernel always belongs to this inverse image. So we have to show that they are inverse images of each other. Yeah, what I have written here, that so we need to show that these two maps, when composed, they produce identity on both sides. Therefore that these maps are these maps give a bijection between them. So one thing what I have just told you, that if X is a submodule of W, then kernel of F belongs to F inverse of X. I mean, if you take K of kernel of F, then F of K equals to 0. Therefore K belongs to F inverse of X, and again other side is true, therefore they are equal. Now what we will show is that we will show that phi compose psi is identity. This implies that F of F inverse of X is X for all submodules X of W, right? Phi of psi equals to identity means phi of psi of x should be x, right? And phi of psi x is nothing but, phi of psi x is phi of f inverse of x, and this implies f of f inverse of x, what is written here. So we have to show that this is true. Now for the first direction, that is this, but this is always true, right? Because f inverse is a map from so v to w is a map, so here is your x. So if you take any element here, inverse image, and its image is always in x, right? So therefore the first direction is true. Yeah, if y belongs to f of f inverse x, then y equals to fx for some x of f inverse x, which means f of x belongs to x, so y belongs to x. And for the other direction, for which we need some work, which says that let us take small y from capital X. Since f is surjective, there exists small v of capital V such that f of small v equals to y. Then your v belongs to f inverse of x, because a v equals to y, and so y equals to f of v, which already belongs to f of f inverse of x, because you have shown that v belongs to f inverse of x. So therefore this is true. And for the other thing also, if you just look into this, that psi of psi compose phi equals to identity, that is f inverse of f u is u for all some modules u of v with kernel of f belongs to u. We have to show that. So by part A, we have that f inverse of f u equals to u plus kernel of f. And since kernel of f belongs to u, that is already given, we have u plus kernel of f equals to u, and therefore f inverse of f u equals to u for all some modules u of v containing ker f. So we have shown that these two compositions are identity, therefore there is a bijection between them, and so you can say that if there is a surjection from v to w, and we have this map, then you can say that all the sum modules from w has a 1-1 correspondence of all the sum modules from v which contains kernel. Now we will look into some problems where your ring is filled. That means your quotient, your module becomes a vector space, right? So yeah, let K be a field, A be a subring of K, such that K is the quotient field of A, and if K is a finite A module, so there are, one second, try to read and understand what the question says, and so do you know what is a quotient field? So you can just look into this if you are not familiar. It can be written as something like this. For integral domain, a quotient field is something like if A is an integral domain, then you can write it as A by B such that B not equals to 0. So this is always a field. So therefore you can assume that it is integral domain as given. I don't want to complicate things, because if it is not an integral domain, then you can just say a dot c b dot c, then it will be 0 in the denominator, where b and c are each non-zero, so it should be a integral domain. It is a typo. Okay, so what we are telling is that if k is a finitely generated A module, then A is k. So A is an integral domain which is a subring of a field, and therefore k is A module, right? So now what I am saying is that if k is finitely generated A module, then this is they are equal. So by finitely generated mean k is a finitely generated A module, then there exist these some finite number of elements from k such that k can be written as this, or similarly it can be expressed by this in some places. Yeah. So first take some time to be familiar with these two conventions, then you can move forward. Okay, so let us start with this. So take small b, which is equals to b1 up to b1 product b2 product up to bn belongs to A with b not equals to 0. Then for each I from 1 to n, we have bxi as b dot ai by bi. Since you can take xi as this, so therefore these are of the form this, and thus bxi belongs to A for all I to n, because these are all elements of A, so their product also belongs to A. Now since k equals to x1 plus up to xn and b not equals to 0, we have, and also we have 1 belongs to k, so there exists c1 up to cn of capital A such that this happens, right? Now multiplying both sides by b square, you will see that b square equals to this, I mean at least up to this. Then what is happening is that you are putting 1b inside and you are putting 1b outside, and this is happening throughout the summand. Now since bxi belongs to A for all I, and ci and b belongs to A, the right hand side is in A, therefore b square belongs to A, right? Now consider 1 by b square, which belongs to k, because k is a field, so obviously its inverse is there. Now since k equals to this, there exists d1 up to dn such that 1 by b square is of this form. Now again multiplying both sides by b square, you see this is happening, and for each I we can write it of this form because you took xi as ai by bi, so yeah, it should be b square di ai by bi. And now since b is of this form b1 up to bn, we have bi divides b, so bi square divides b square, thus b square by bi belongs to A, right? Which means b square, I mean this term belongs to A. this term. So therefore 1 belongs to A. Now since 1 belongs to A, we conclude that A contains the multiplicative identity of K. Now for any at least we have seen that it contains the multiplicative identity. Now we will see that it contains every element of K. Now for any A by C of K, we have A by C of K is of this form, ax1 plus up to axn. So again you can write it, you can find EI from A such that this happens, and multiplying by B, that is B1 up to Bn. So you can see that this happens that AB by C equals to E1 of Bxi and something, and this belongs to A because EI belongs to A and your Bxi belongs to A, so A by C belongs to A. And by a similar argument, if you put BC in place of C, you can see that 1 by C belongs to A for any non-zero C of A. So therefore what we have seen that A belongs to your A and 1 by C belongs to A. So therefore A by C belongs to A. So we are done. So you can say that capital K belongs to A. So A is a field, and yeah, A equals to K. Now a simple corollary from here, it follows that you can show that Q is not a Z module. So this is kind of big, no, not big, this is 2 or 3 lines. So can you look into it and say that if you understand or not? I mean, this is one liner, there is nothing to see. So if it was finitely generated Z module and Q is already a quotient field of Z, so it would be something like this, Z equals to Q, but this is not true, right? So yeah, therefore Q is not a Z module. So this is an interesting question for PhD interview or also like NBHM, NetGet type exams. So this is nice. And there is another question is that if A is a subring of K and if A module K is finite, then A itself is a field. So I will give this to you as an exercise. The answer I am already providing, so check yourself that if you can understand this, and if not, we can discuss this in the next tutorial, or you can just send me a mail again. Alright, so if you have any question, you can ask me now. You don't have? Alright, so okay, we can stop this here, and thank you.
So I have a query about the logistics of the lecture.
Sorry?
I just wanted to ask whether the final exams is going to be subjective like the assignments, or is it going to be MCQ based?
MCQ or like is this thing you are asking?
Yeah. Because the assignments we submitted were all subjective.
Oh, I think it will be subjective. I'm not sure because I am not attended this kind of course before, and the exam thing I am not handling.
Okay.
So it is Siddhi is handling this, so you can mail her. I think her contact information is given in the community group, community mail.
Okay.
Yeah,
Okay.
okay,
Fine. I will mail. I will
okay,
mail.
okay, okay.
Okay.
Okay, thank you for joining everyone. So, good night.